Okay, so let's speak a little bit about explained and unexplained variation. So SST is the abbreviation for the total sum of squares. This measures the variation of the y values around their mean. SSE is the error sum of squares, the variation attributable to factors other than the relationship between x and y. So in a lot of statistics, we always assume that, not always, but in some cases, like when we don't have a very controlled experiment, or there's something about our design that we can't necessarily prove causation, we try to measure, we try to leave some room for error, right? Like when we think about our 95% confidence interval, we're leaving 5% room for error, which is acceptable. And it's not very high, so we're okay with that. With SSR, for example, regression sum of squares, it's explained variation attributable to the relationship between x and y. And again, I don't expect you to like memorize any of this stuff. I'm just giving this to you for your information, and then we'll be able to focus on some other stuff when we speak about it again more. All right, so some explained and unexplained variation. Total variation is made up of two parts. The total sum of squares is equal to the sum of squares errors, sum of squares error, and the sum of squares regression, right? And then this is what the formulas look like. So average value, right? So this is the average value, right? Because we know we're doing the sum, we're taking the difference and squaring it. The average value of the dependent variable, right? Dependent variable, meaning the outcome variable, our y, right? So we usually think of our independent variable, or the variable that is our predictor variable, as x, and our outcome variable, or the variable that is dependent, as y. So these are all explaining our outcome y. So that's the average value of the dependent variable. Yi, right, is observed values of the dependent variable. And I is an estimated value of y for the given x value. Okay. So coefficient of determination, r squared, right? This is going to be one of the more important values that you're going to see, I believe, in your output. So this coefficient is a coefficient of determination, and it is the portion of the total variation in the dependent variable that is explained by variation in the independent variable. Coefficient of determination is also called r squared, and this is denoted as r squared, and this is what this coefficient is comprised of, right? The SSR over the SST. So r squared, you want it to be greater than or equal to 0, but less than or equal to 1. And we may look at r squares in the lab. I'm not really, in any case, right? So the sum of squares explained by regression divided by the total sum of squares. So in the single independent variable case, the coefficient of determination is equal to r squared, right? The coefficient of determination is equal to the simple correlation coefficient. And r squared is equal to coefficient of determination, and r is equal to simple correlation coefficient. So here's some examples of the approximate r squared values, right? Yeah, and this is what I was talking about. So if you have r squared is equal to 1, then that is a perfect linear relationship. Right, r squared equal to 1. 100% of the variation is in y is explained by the variation in x. Right, this is what r squared of 1 means. It's just a perfect linear relationship. Now, when your r squared is between 0 and 1, there is a weaker linear relationship between x and y, but not all of the variation in y is explained by variation in x. Right, so in linear regression assumptions, the linearity, the population regression line is straight. Homoscedasticity, the standard deviation of error values, is constant across values of x. So this is an extension of the assumption made in ANOVA. And then number 3, approximate normality for a given x, the y is approximately normally distributed. And number 4, in the independence, when it comes to independence, we have n independent pairs of observations, right? So xi, yi, and then I is going to be anywhere from 1 to whatever your n is, how many values you have. So compactly expressed, y is equal to the beta 0 plus the beta 1 times x, and the error term, where there error is n. Anyway, you don't really need to know this. I'm just making sure you guys know that your outcome in your regression is explained by this formula. But if you want more information about this, I have actually calculated this by hand, but that was just because, I was learning it and wanted to understand my results. So yeah, these are the 4 assumptions that you want to pay close attention to when you're doing your linear regression analysis. The link between correlation and regression. So if X and Y are normally distributed, right, with a correlation row and the regression assumptions hold, right, then for the sample, beta 1 is going to be the standard deviation of Y divided by the standard deviation of X times, right, rho, right? This is like the Greek term I was telling you about earlier. Beta 1 is equal to standard deviation, right, S of the sample, Y, right, the standard deviation of Y in the sample divided by the standard deviation of X in the sample times R, right? This is the estimate from a sample, right? So this is a population parameter and this is a sample statistic, right? The beta 1 with the hat. All right, so here's a linear regression example from our textbook. And it tells you here the body measurements. Let's see what this is about. The scatter plot and least square summary below show the relationship between weight measured in kilograms and height measured in centimeters. So the height is along our X, the weight is along our Y. So this is our predictor. We're trying to say based on your height, this is your weight, right? Predictor, response. And these are both 2 continuous variables. So they ran a regression analysis using SPSS or R or whatever software they decided to use. And this is what the results look like. You get an intercept, right? The intercept, like I explained earlier, is the value of Y when your independent variable is equal to 0. So this is the intercept, the estimate. But the actual results here is the height, right? You want to know for the weight, what's the height prediction? And it gives you an estimate here. I believe that this is a regression. So this has to be the beta estimate. So for every centimeter taller that you are, right? And this is what I was trying to explain to you how you interpret this. For every centimeter in height taller that you are, you will be 1.0167 kilograms more in weight for every increase in height. That's how you interpret this estimate. Then they also give you the standard error, they give you the t-value, and then you obviously get your p. This is the same as saying p-value over here, and it's way less than 0.05. So we would say, okay, this is statistically significant, right? So last thing I just wanted to point out really quickly before I wrapped up this lesson and get into the lab is there is another type of regression. There's actually a few statistical inference techniques regarding regressions. And when you see, or hear about risk predictions and modeling, these are the analyses that they're specifically talking about. I won't go into all of them because there are quite a few. And this is that's also somewhat higher level. But logistic regression is very similar to that of linear regression. The only difference, right, is when we're speaking about a simple linear regression, as we did in this lesson, we're speaking about our response variable or our outcome variable being continuous. In logistic regression, this is a statistical inference technique to analyze data that has a proportional outcome rather than a continuous one. So this won't be, again, part of our lab, but if you're interested in more, you are welcome to check this out, simple logistic regression, and reach out to me with any questions. Thank you, and I look forward to seeing you in lab.